Hey guys, welcome back to another episode of Simuleos. Today, we're going to be working on a new simulation. So what are we going to be working on? Well, after the vote on Friday, we had a couple of responses for a couple of different things, and honestly, I spent the entire weekend working on that video, which was recently out on YouTube. If you're interested, I can send you a link. But yeah, so since I spent the entire weekend working on that, I really didn't get so far in the studying department for the next simulation. So what we're going to be doing is we're going to be working on octrees. Hey Edge226, what's up? Let's go ahead and describe what those are and what we can do with them. So let's go ahead and do Zernal and go from there. So first, octree. Then we'll talk about the applications. The idea behind an octree is pretty simple, so I'll go ahead and draw it up here. Octree. Now, it is technically octree, but they kind of ignore one of the T's just because, I mean, I don't know. They just do. It's very similar to what's called a KD tree, if you've ever done anything with that. But the idea here is relatively simple. We have a box. Okay, that was meant to be a box, but I'm not drawing a box at all. We have a box. There we go. And in the box we have a whole bunch of particles. So maybe one here, 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 and there, or something like that. Now what we do is we draw a straight line along the half. Another one along here, and the reason these guys are called octrees is because it's assumed that this will be in 3 dimensions, right? So in 3 dimensions we'll have an additional cut along the z-axis, right? So for here, let's say that these are quadtrees. Okay, so then after the cuts, what we try to do is kind of localize the particles. So what we're going to do is we're going to continually make cuts along the halves, cut these guys into quarters, until eventually all of the particles are in single boxes. So we'll do something like this. There we go there. This guy already has his own box. Something like this. And that guy already has his own box. So in this way, we've given all of the particles their own box. And now we represent this tree in the following way. I'm glad Edge226. Sorry about that. Okay, so here's how we represent the tree. We have a central node here. And we have 1, 2, 3, 4 over here. And each of these nodes have 1, 2, 3, 4 associated with them. Hey, is that your fan? So we are going to, let's say up here, have a single node. Over here I have a single node. And then over here we have 1, 2, 3, 4 with, let's say, this guy and this guy full, and this guy and this guy empty. So I guess we'll cover the full ones in black just to say they have a particle. Something like this. And then down here we do something quite similar. 1, 2, 3, 4. I forgot to draw the node. And then we say 1, 2, 3, 4, where these guys are full. And in this way we've represented the position of the particles kind of with a tree, right? And you might be asking yourself, why would you want to do this, right? Under what situation would it be easier to represent the particles in a 2 or 3D simulation in a tree? Well, it's actually much easier for a number of different reasons, one of which has to be page, new page before, the Barnes hut n-body simulation. Now, for this, I think the easiest thing to do is just go on YouTube and just Google Barnes hut, or just to Google Barnes hut over here. So let me do Barnes hut, and let me see. Explicit results. Okay. I don't want to learn more on or undo. So let's do videos. Okay, so I'm going to take a look at this one. Hopefully there's not so much background music to it. The idea is that we have, let's see, maybe I can full screen that. Okay, the idea is that we have a whole bunch of particles, and they're all acting as their own individual units, and we're allowing them to basically move around, similar to the MD code we did before, but here we have, you know, millions of particles, or thousands of particles instead of what we had before, which was hundreds of particles. So the reason we're allowed to do this is because of how we're storing the particles, right? Because otherwise we have to calculate the force of every individual particle and all the other particles, and it scales as n squared. But if we represent everything as a tree, what we're allowed to do is we're allowed to kind of clump particles that are far away together, because these are all just kind of inside one internal node. So this means that we can treat all of those particles as one big particle for particles that are far away, which allows us to do much bigger simulations than what we were doing before. And that's kind of the idea. So, hey Guster and Marion, what's up? That's kind of where we're going. Sorry, I probably shouldn't have that up. Good. I don't think there was any sensitive information on that, just my YouTube statistics. I checked it just before stream. Okay, there. That's kind of where we're going. However, we've got a lot to do before we get there. So I guess we'll just kind of hit it one step at a time. Now there's a lot of stuff that I kind of glossed over here, but we'll kind of get into while we're doing the programming. So I don't think it's, oh my gosh, I'm so tired. Sorry about that. So I don't think it's absolutely necessary to talk about here. I think, in fact, just describing all the particles as a tree, I think that's enough to go off of, and then we'll go from there. And we'll see how difficult this is to do. On the one hand, it could be relatively straightforward. On the other hand, it could be relatively difficult. I have absolutely no idea. So we'll see how things go. But again, that's about all there is to it for now. We'll go ahead and code up the tree part today, the octree stuff, and then we'll work on the force integration stuff as soon as we're finished with the octree stuff. I think we should finish the octree stuff in like a day or two, and then we should finish the force propagation or force integration is what I mean in like a day or two after that. So maybe best case scenario we're done on Friday. Maybe. No idea. We still have to do the visualization with Blender and everything, so and maybe we need to do something other than Blender, because if we have so many particles, maybe Blender's not the best choice. No idea. We'll see how that goes. Okay, so let's pop this over there, pop that over there. Now again, octree is specifically for octrees are specifically for three-dimensional data. Quad trees. Yeah, I know. I mean, I always kind of put a positive estimate in there, or an impossible estimate rather, of what I think, oh, we'll be done by Friday, and it's done like 4 weeks from there. So, I don't know. We'll see how far we get. So let me CD back into a directory. I was in the old demon directory a second ago for the Maxwell's Demon stuff. Now, we're starting a new simulation, so we need to create a new directory. Let's do make directory, and we're just going to call it Barnes hot. I guess capital hot. Why not? Let's CD into Barnes. Here we are. Hey, NNG, what's up? So let's go ahead and ls over here. We have nothing there. Let's CD into the appropriate directory over here. Projects, Simuleos, and of course, Barnes hot. Okay, so let's go ahead and open up the new file. So open up Barnes. Well, yeah, that's okay. We'll call it Barnes hot. .cpp. Okay. So what are we going to have to do here? Let's go ahead and open up the file like we normally do, starting... Okay, here we are, Barnes hot.cpp. Okay, so now the question is, what do we actually need to put in here? We have to have a whole bunch of different functions for octrees and things like that. And we also need eventually force integration. The question is, do we want that in the same file as everything else? We'll kind of get to it when we get to it. So purpose... basically, we start with an octree, then we move and body, body simulator. Okay, good. I'll leave some notes when we get to them, but right now I don't think we have very many. And let's go ahead and include what we know we're going to need. So for now, I know we're going to need, include IOStream. We're also going to definitely need random for the start. What else do we need? For now, I think this is it. We'll add more as we get to it. Now, in terms of the makefile and stuff like that, for now I'm not going to be running with a makefile. I'll run with a makefile in just a bit, once we kind of have the libraries all set up and I know exactly what we need to put in there. So, first things first, let's go down here and let's go ahead and do int main. Okay, so we have a main, no problems there. And I'm just going to go ahead and separate this guy up because I know we're going to run into some issues otherwise. So again, guys, if you have any questions, comments, concerns, let me know and I'll totally address them as soon as I see them in chat. And of course, I did have one major criticism on the last video that I just put out there. And that was that I guess it wasn't as understandable as I'd hoped it would be. So I guess I need to get better at that. I mean, what's the difference between printf and IOStream? I thought they would be the same thing in terms of speed. 1 second. Is one actually faster than the other? Oh, I didn't know that. Holy cow, this whole time. 1 second. I had no idea. Interesting. Okay. So then I have to have one more up here for functions and things. Huh. Well, I'm really bad at using printf. So we'll use IOStreams and then we'll go from there. Honestly, I'm terrible at using printf statements. Like, I just can't use them. So let's go here. And what do I want to do? I want to... Man, I'm super surprised. I would have thought that, you know, they would have been the same speed. So here we'll say just structs or something like that. Just so I can easily find it. Okay. So all this stuff up here, let me see. Let's go ahead and include that down here. And we're going to say include cstdio for printf, which... Okay, so we'll do that in a bit. For now, since I'm really bad with printf statements, we'll stick to cout statements and we'll go from there. Let me think. They are not, but go different values for different sizes. 1 second. Marion, which comment are you referring to? So they're not, but go different values for different sizes. Are you talking about printf and cout? Or IOStream? Okay, so let's go ahead and get started here. We know we're going to have to create a couple different functions, so let's go ahead and start at the start. So let's see. In order to do the octree stuff, oh, I see. So is it that... What does that mean then? Does that mean that printf works better for large scale output? Or does it mean... I don't know. Okay, so we know we're going to need a couple different functions. So let's do a function to create a random distribution. Wow, I don't know what I was trying to spell there. Distribution of, let's say, particles for octree. Okay, so we're going to say, what do we need to return here? We could return a vector of doubles, but I think instead we need to create a struct here. So we're going to say struct, and we're going to call it position for now. And inside of here, we're going to have, let's say, double x, y, and z. Okay, so then what else do we need? Okay. So we're going to go down here, we're going to say we need an std vector of, let's say, positions. And let me run up here and add in vector. Okay, that was, what? I am just not spelling anything right today. So we have vector positions, and we're going to say, how about create? Random distribution probably works okay. Yeah, new project, Bostic Mall. So it's gonna be a little bit slow to start and basically pick up in a little bit. We'll see how far we go. I'm kind of excited for this one, guys. The last one we were doing kind of basic physics, you know, like in a way, optics is something that people can intuitively get. At least the form of optics that we were doing with geometrical optics. Here we're doing something a little bit, well, it's still kind of easy to understand because it's basically just the gravitational like force spread throughout a number of different particles. But the sheer number of particles we're working with here is kind of interesting, right? So for the most part, with all the MD simulations I've done so far, I've kind of maxed out at like 40,000 or something like that. And I want to see if we can beat that. You know, the reason we've kind of only gone to that number, and that number is still quite large, is because of the way that we were doing the force integration. We had RK4 or RK2, Runge-Kutta 4 or 2, and the idea was we just kind of ignored particles that were outside of a particular range, right? Here, we should still be able to have an accurate simulation because we're doing something, a rather large n-body simulator. And I'm actually really interested to see how far we get here, you know, to see just how many more particles we can simulate. Because if we can simulate like hundreds of thousands of particles, that's pretty dang cool. Now, I don't really know what we can do with it except like do some sort of gravity simulation, but we could also do like dusty plasma simulations and stuff like that too. I don't know, just random things we could do. I don't know what we'll do with it yet. So I kind of just said, you know, if you look at my stream, it kind of says like space trees or something like that. And I think in the description I wrote like gravity simulator or something. I don't know what I wrote, but we'll see. So what are we doing? We first need to create the random distribution for the octree. So what is this going to be called? I guess it's going to be called create random distribution. I feel like that's not the best way to do this. Let me see. Ow. Jeez. I cut my finger the other day. Let's see. Random distribution. Maybe this is fine. Whatever. It's okay. What do we need? We need the box length. So we'll say double box length. And this is going to be basically how much space we're going to take up. Now all I'm doing here is I'm going to create basically a random distribution of particles in XYZ along the box. So let's go down here. Let's go ahead and add in the function. So we're going to say std. Oh, we'll just copy this whole thing. We'll see what happens. Bam. Okay. So let's go here. And there. The first thing we need to do is create the vector of particles. So we're going to say, how many particles are we going to have? Well, I don't know yet. So let's also in here have a number of particles. So int, I guess we call it number. Particle number would be a little bit better. So let's say part number, pnum. That's okay, pnum. Yeah, let's do it, pnum. Okay, so we're going to go here, int pnum. Okay, so now we're going to say std vector. Let me think here. It's going to be a vector of positions, right? And we can do a whole bunch of things with these structs and stuff right now. But for now, we'll just kind of leave it all simple, and we'll kind of add more and more complexity as we go along. So first thing we need to do is we need to say vector of positions, and I guess we could call it particle position, something like that. Particle position should be okay. So we'll call it particle P position. Why not? I feel like this is not the best name though. What else could we name it? Create random distribution. Let's see, position. We said P number before, but I don't really like that one. So let's do P position or something like that. That should be okay. Now we need to give this guy an appropriate size. So let's see. I'm not sure the best way to do this because the last time I did this, let me think. I was told I should just reserve all of the space. However, I'm not sure exactly under which situation I should be reserving the space and under which situation I should just go ahead and give it an appropriate size. So let's go ahead and do this and then say p position dot reserve. And I don't know if this is exactly right, p number. So let me just go ahead and see if this compiles. So let me do G++, Barnes Hut, .cpp. It seemed to compile. So I'm going to assume that this is an okay way to do it. New project, point mass. A point mass hopefully will be easy. Hopefully. Probably not though. Okay, so now we have our shoot, what am I looking at here? We now have our vector for all the particle positions out there. If you're adding elements one by one to an empty vector, reserving will always be faster. Okay, fair enough. That's what we'll do then. If we do it in parallel, does that change? Okay, so let's see. Now we have to do all of the random stuff. And I'll be honest, guys, I always forget how to do random stuff. So what I did is I wrote it down. Hopefully, this will kind of work out. Worst case scenario, I just look at old code that we've already written, which happens more frequently than it should, where I always kind of forget what it is that I'm doing. Given the size in the constructor is useful when you want to initialize all elements in the vector at a given value. Fair enough. Okay, so here's what we're going to do. We're going to say, let me see if I can move everything on this desk around. Here, good. We're going to say this. We're going to say static. First I need to comment some stuff in. So creating vector for particle positions. And I'm going to say p position. Okay. And in the end we're going to have to return it. So let's do return p position. Okay. Now let's go here. And let's do this. So we're going to say static creating random device to place particles later. Okay, so here's the thing. I'm going to assume we're in a cube. Now I realize that might be a poor assumption, but that's fine. I do not... Wait, Simuleos. I do that all the time as well. Okay, I want to do something and I forgot exactly how it was done because Bash is never the intuitive way. What file as the example? Yeah, trust me, especially Bash scripts. Holy cow. You're totally right when it comes to Bash scripts. Like, no matter what happens, I can never remember how to do anything with Bash. Now, that said, I know some people are great with it. For me personally, I don't know. I also have that trouble with a lot of CUDA kernels. They're just not intuitive for me. I've been trying my best to get better at writing them, but just every once in a while, they go right through my ears. Don't bash the Bash. I'm not bashing Bash. I mean, it's definitely useful. It's just every once in a while, gosh, I have trouble using it. Which is fair enough. I have trouble using everything. So let's do static std, and then we're going to say random device. Random device rd. We go down here and we're going to say seed equals rd, and I think I already screwed up, but I'm just gonna go ahead and compile this. Let me write this over here. Yeah, that's what I thought. I think it needs to be int. Okay, that seemed to work. We'll see what happens. Okay, next we say static std Merlin Twister 19937, and then we're gonna say gen seed. Oh my gosh, what am I doing? There we go. Add a semicolon. Now what do we do from here? We now say std uniform real distribution double, and we're gonna say uniform real distribution of doubles. There we go. And then we give it a like distribution or something like that. We give it a variable for this. So we'll say box distribution. Okay. And then we give it a range for which it will work over. And since we have the box length and we have the origin, I'm assuming is going to be at 0. All of these guys, I suppose, will just be along the following values. So let's go up here. Let me think the best way to do this, I suppose, is just this. So we'll say negative box length over 2 divided by 2. And how about times 0.5? Makes it a little bit faster. Oh, well, if I can find the correct... Here we are. Oh my gosh, what is happening? Okay, here we go there. And then I'm gonna bring this down here real quick. And then box length times 0.5. There we go there. Add a 0 in here. Good, so now we have our box distribution. Let's go ahead right here. G++ again, just to make sure I didn't screw anything up. Everything seems to be fine right now. We'll see what happens in a bit. Good, so now we just go through all the positions, and we go from there. So now, iterating over all positions to create random points. How about all particles to create random positions? Positions. Sorry about that, had to sneeze. Okay, so we have our vector. We can do this in a number of different ways. I'm just going to do it this way for int I equals 0, I less than. And again, we could just iterate through everything with auto. Let's try that one. So we'll say auto. I guess we'll call it P. In, let's say, P position. Okay. And now we're going to say P dot X is going to be equal to is going to be equal to, let's see. But I occasionally bash about bashing bash. You know, I don't know what it is, but I kind of like, I don't know. Hey, I care. What's up? I kind of like a lot of the odd names for different things. Why is bash called bash? It's like the born again shell. What does bash stand for again? Something like that. I don't know why, but I like how a lot of people in the Linux community and computer science community, heck, scientific community actually, really just, they like creating weird names that form some cohesive word in the end. You know, like bash obviously stands for something, but you know, no one knows what it stands for. It's just bash, you know? I kind of like that. It's kind of neat. Okay, so p.x is going to be equal to, I think, just box distribution of the generator. Yeah. Okay, let's see what happens. P.y. Oh. Maybe I'm the only one. Equals box distribution of generator. And, oh, I know some people do. Z is going to be equal to box distribution. Let's do distribution of generator. Okay. Write this, go over here, make. Oh. G++. Okay, so now what I'm going to do is see out everything as we go here. So let's do that real quick. So we're going to say std cout p.x, new tab, p.y, new tab, and p.z, new line. Okay, let's go ahead and write this. Go over here and let's run that. Now let me go into main just to check what we have so far. I don't know, let's just call the function. Yeah, fair enough. So we're going to say create random distribution. Yeah, I guess that's it. So let's do vector, std vector of positions, and we will say the vector of positions is going to be called, why not p position again? Sure. It's going to be equal to create random distribution with box length, which we'll say is 0.5. 0.5. Let's call it 1. Box length is 1.0. And then we'll say P number is, we'll do 10 for now. Write this, go over here, and let's run the G++ command. Create random distribution. Choo-choo. Expected initializer before. Oh, I forgot an equal sign. Now let's try that. Good. Run a.out. Screwed something up. Alright, need to learn about TCP IP stack so I can do homework and just vegetate on WoW until class on Wednesday. I'll see you around, that your fan. Thanks for coming in. Okay. So something went wrong here. Seems pretty simple, so I'm not exactly sure what I did wrong, but I will take a look at it in just a second. So we have this int main. Let's go to right here. And let's just output something real quick. I guess we'll... What? This is like the simplest code ever. 1 second. Let me go here. std cout. Iterating, creating random positions. There we go. New line. Okay, over here. Now let's run G++. A.out. Creating random positions. Did I screw up on something? Let me see. Because we're clearly not going in here. Let me see. P position. Reserve P number. Let's do it another way then. 4. Int I equals 0. I less than P position. Dot size. Then we'll do I++. Or plus I, whatever, doesn't matter. We'll change all these to P position. Oh, 1 second. P position of I. Just for now. Oh, I need an ampersand? Ah, shoot. My bad, guys. That's me being an idiot. Let's try that. Auto ampersand. P position. Let's try that one. P was not declared in the scope. Auto. Oh, I need to say P. G++. A.out. Creating random positions. With regular order, you're making a copy. 1 second. Okay, let me check something. Let me go into another file where we've done these types of loops before. I apologize for this, guys. Archive, Maxwell's daemon, or molecular dynamics, actually. Then daemon. And we will go into daemon.cpp. Let's scroll down just a little bit to where we did this. Auto P left data. Yes, that should be right. So this is exactly what we should have. Well, except the ampersand's like, whatever. Doesn't really matter. Okay. So, good. Does that really change anything? The ampersand in the wrong spot? G++, A.out. For quick rule of thumb, in range-based for loops, always use auto and or const auto. Before you modify values inside the loop slider, you don't. Fair enough. Okay. 1 second, let me see. Creating random positions for all. 1 second. P position dot size down here. Particles. Exclamation mark, because we are excited. G++, A.out. 0 particles. Okay, that's the problem. We are creating the vector incorrectly such that there are no particles in it. That's fair enough. So, let me see. Where did we do the reserve stuff before? Oh. Okay, it's fine. We'll just do this another way. Screw it. P number. Let's go down here. And we're gonna do this. Hey Krams, what's up? We're gonna say for. I just put a for loop in a for loop. I'm doing great. Int I equals 0, I less than p number, then I plus plus. And this needs to be a size t. Oh no, an int, because p number is an int. Can't you just call p number? Or use that ctor? Can't you just call p position p number? Yeah, that's basically what we're going to be doing. So let's see. We're going to do... Yeah, again, I am trying to be efficient with this, but at the same time, yeah. So let's do this. We're going to say, I guess we'll have to do this. So let's go up here and let's call temp position. So we're going to say position, temp position. Okay, so we'll say temp position dot x, temp position dot y, and temp position dot z. Now we're going to say, where are we here? Should be p position dot pushback, and we want to push back temp position. Something like this. 1 second, underscore. Let me see. Pushback or place back is the right course of action here. Let me see. Oh, right, my bad. No, I mean, it's fine. Honestly, the other way would work too. Not a big deal. Not much, just programming, hunting for an error that only appears in my test scenario, really never with production data. So actually, at work right now, I ran into this error that I've been trying to fix for days. Like, seriously. The best would be giving a constructor to position, taking x, y, and z, and calling p.position and place back. Box distribution generator, box distribution generator, box distribution generator. Let me see. Best way would be giving a constructor position, taking x, y, and z, and calling p.position.mPlaceBack. back. Box distribution generator. Okay, I see what you're saying. Okay, yeah. Wait. Yeah, I guess that's fair enough, Gustorn. Okay, so let me see. Best way of giving a constructor position, taking... Yeah. So let's see. Constructors to this guy. Let's go ahead and do that. Let me go into another file so I don't screw up again. You add a point, and you generate an XYZ for that point. Yeah, that's fine. Let me just go ahead and quickly put a constructor into position. So what are we going to do? Let's go into geometrical optics. And what do I want here? I want geometrical.h, I believe. That was... Let me look for vector. Here we are. No, that's not quite what I wanted. I want a struct. Here. Struct array. Vector PV. Struct simple, structs here. Let's go here, quit. And let me try something else. Maybe optics visualization.h. Let's see, where are we here? Vec, here we are. Okay, let's go here. And let's do the following. So we're gonna say position. Sorry about this, guys. Again, I have a specific subset of things that I remember, but outside of that, I am definitely a goldfish. 1 second, Y. And then z of 0.0. Okay, now we do this. Good. And it should be, we do the same thing down here. So let's do position. Reading in 3 different things. So we'll say double, doable, double, x naught, double, y naught, and double, z naught. And then we'll say x of x naught. Spending way more time to fix errors with the tests than the real errors. Yeah, I know that feeling too. So let's say x naught, y of y naught, because why not, and z of z naught. and then these guys. Okay, that should be okay. So let's go ahead and write and quit here. Then we'll go down here and we'll do exactly like what Guthrun said. So let's go here, DD that. Now let me see. With real bugs, at least you have this got you haha feeling afterwards. This kind of bug is just great. Now I did get to spend another 3 hours on stuff that never matters. I mean, I don't know. It does matter if people look at the code, right? So what do I want to do? I remove the temp position. So let's do this then. We'll say implicit back. And actually, Guthrun, I'm not actually sure the difference between implicit back and pushback. So let's say box distribution generator. Gen. Box distribution. Gen. And box distribution. Gen. Okay. Man, super sneezy today. Okay, there we go. Let's write this, go over here. Run G++ again. P.x, of course. You just go ahead and remove that. Implicit constructs the value. Takes a temporary and copies it. Oh, I see. Thanks, Marion. Okay, so let's go down here and let's output stuff. Okay, I see. Appreciate it, guys. So let's go ahead and do p position of i.x. And let me just stdc out some stuff. stdc out p position i.x. Then we want p position. I forgot a p. p position of, let's see, i.y. And new tab. P position of i.z. And new line. Okay, write this, go over here, run G++. TD, of course not, because we need an S. Now let's try that again. A.out. Good, okay, so now we have 10 random positions. I forgot a tab. Let's go back and add in that tab. Oh man, I screwed everything up there. 1 second. Okay, and I'm just gonna drop this guy down to the next line. Let's see. Also get a bit more used to it. Same thing with printf. Let's see. Good, fair enough. Let's go ahead and do that one too. But first, let's write this one. Do G++, a.out. Good. These look like random positions between 0.5 and negative 0.5, so that seems good to me. Now, let's go ahead do the printf thing, because I need to... I mean, everyone else uses printf anyway, right? So let's do this. What is this? Long float? Is that what that stands for? 1 second. Then x. So then we need p position dot x, p position dot y, and p position. Oh, fair enough. Dot z. Okay. Now we'll do this, and we will say, what do I want here? I want to say I, and I. Let's go over here. Let's run last G++ command. Compiles, run a.out. Good, okay, seems good to me. Again, random numbers, everything seems fine. Now we have to start thinking about visualization. All right, good, thought about it. Let's move on. So next we need to actually create our awk tree, and the awk tree is going to be a little bit challenging to create. So we're going to need to first create a structure for it. So let's go down here, and we're going to have to say struct. I guess I'll just call it awk tree. Okay. So for this, we're going to need a couple different things. So we're going to need obviously a node, and we're actually going to have to point to all of the different nodes, right? So let me think. What we can do is instead just call this node like we did before. So we'll call this node here. And the node goes down here, and it holds node. Now here's the part I'm not quite sure the best way to do it. We're gonna have to have 8 nodes within each node. And I'm trying to think, how do we name these nodes, right? Because on the one hand, we could just do something like this. Up, node. Oh, I guess it'd be easier to do it here. Star down. And so on and so forth. You know, like up, down, gosh darn it. Up, down, left, right. Or like north, south, east, west, or something like that. But that doesn't really appropriately describe all the boxes, right? Now we could also create a vector of nodes that we're pointing to and just know the numbering scheme. That's another way to do it. Or a map, I suppose, but I feel like a map would be a little inefficient. I think the fastest way is just giving everything an individual name. And for the record, guys, in case you're not sure what I'm talking about here, in the end, the octree is basically a way to take a 3-dimensional box. So let me go ahead and draw a 3-dimensional box. Here's a box here. Let's redraw that one. Okay, so here's a box here. Oh my gosh. One second. Let me see. There you go. Got it. Let's draw a line there, 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 and there. Here's our box. There. We'll put a whole bunch of particles inside of it, which I will draw in red. Just these are all inside of the box. Okay. And then what we do, let me see. That's exactly what it stands for. Printf tricked is nicer output. I see. Okay. So here's what we need to do. We need to split this box into 8. So I'm going to do this in blue, I suppose, just so we have a whole bunch of different colors. We split it first this way, then this way, then finally this way. Oh. Let me try that again. So here's the center of the box. Let's try to hit the center of the box, something like this. Okay. Hit the center of the box again, something like this. And then hit the center of the box again, something like this. Okay. So we'll split it into 8 parts. And then, after splitting it into 8 parts, that's not a very good picture, is it? Anyway, I tried my best. So we'll split it into 8 parts, and then after splitting it up into 8 parts, what we need to do is we need to give each of these guys some components. So like I was saying before, we'll have our node. And again, we could just say node star, and we'll say, I don't know, up, left, up, forward, up. I don't know. This will pad positive numbers with a space so they'll line up with negative numbers and round each value to a position of 3. Oh, fair enough. Okay. So we could say up. Or we could say north, northeast to designate like this box up here, and north, southwest to designate like this box down here. Oh, southeast, I suppose. So on and so forth. I just don't know the best way to name this. So if you guys have opinions, let me know. I'm just going to do it in kind of an unintuitive way for now. And again, we could just do this with vectors. We could say we have a vector of node stars, I suppose, of pointers to nodes. And we have 8 of them in every single node. So every node has 8 other nodes that it's pointing to. Then it also has its parent node. So let's go here. We know for a fact that we're going to have a parent node. So let's do that. Say node star parent. Okay, we're also going to need, oh, my bad. We are also definitely going to need some sort of position. So a position of the node itself. And this position will just be called P. Sure, fair enough. Then we have a box length. So we'll say double box length. Again, these boxes will get successively smaller and smaller as we go through. But this should allow us to relatively easily find all the particles, I think. Okay, if no one has any idea for the naming convention, let me think. How do we want to do this? First, let me get a quick sip of water. I forgot to refill my water bottle before today's stream. Could run out. By the way, I realized I go through like 6 liters of water a day. Like, this is a liter of water. I go through it a lot. Every single day. And other people like have trouble just drinking water in general. And it's just like, come on, how do you not drink water? Okay, so let's see. I don't think any of this really needs to be commented in. But let me very quickly put down here. Struct for position of particles. And octree nodes. Okay, and down here we'll say struct for octree nodes. Okay, so in the end we'll just have to return the root node like we did before. We're gonna need a depth first search algorithm again like we did before. So let's go and get these nodes up. So let me just do it this way. We'll do the notation I just did before with the north, northeast, and south, southeast type of thing. Maybe that'll work. Yeah, well, let's do that. This is an awful naming convention. Let me go down here and comment this in. Child nodes are ordered based on cube. Let me see, based on their position within the cube. First, split into north and south. Then, it's not ordered, let's say named. Named, there we are. Then, into north, south, east, west. And west. Okay. So we'll say north, northeast. Should they be capital? Why not? Okay, so then we'll do north, southeast, north, southwest, north, northwest, south, southwest. I really don't like the name convention, guys. I already hate it. South, southeast, south, northeast, south, northwest. This is awful. I think a vector. Let me see what the vector of nodes would look like. 1 second. Let's go ahead and add in spars to all these guys, because they are, in fact, pointers. Okay. Okay, now the vector of nodes would look something like this. STD vector of, let's say, node star. And then we'd have to have it of size 8, so we'd say, I guess, children of, I guess, immediately create them all as size 8 or something like that. Or I guess we do it this way. Use an array. So you'd want me to do, let me see, the following. Notes are children 8. What is it? Is this the notation? No, I think it's, I think parentheses was right. Let me just very quickly run G++ because that'll tell me. No, that is incorrect. However, it says I missed a semicolon. Node star children. Oh, 1 second. And then I want 8 of them. Dang it! I had it right to begin with. It's me using Fortran. G++. Okay. Yeah, the children ate it. Ow. Dagnabbit, I keep hitting my finger. I'd prefer stdarray node 8. What's the difference between doing it that way and doing it this way? Sorry about that, if I could ask the question. Okay. Yeah, so let's do this. We should probably keep track of the order in which we're working on all the nodes, right? So let me go ahead and comment that in. So let's go here. I think I like the array better. So let's go here and let's say nodes are ordered the following way. Split the cube into north south, then into north south east west again, and we're gonna say array stores its size. You can use it in range base loop. Yeah, fair enough. Okay, so let's go up here. What do I need to do? Include array, I believe. Oh man. There we go. I mean, yeah, we always know it's going to be 8. Is there any type of overhead that comes with the array library? We'll leave it here for now. Honestly, I think we'll leave it here for now. Because it's always going to be 8, right? It's an octree. I suppose we could create a template for octrees and quad trees if we wanted to do something 2-dimensional. But for now, I think we're going to be sticking with 3-dimensional. I don't see a reason to drop back to 2-dimensional. In the end, this could be a number of different things. It could even be a Dusty Plasma Simulator. No. So here's the order. We're going to say 1 is going to be north, northeast. So that's going to be, yes, so the first quadrant over here, then we're going to read over like that. So then we're going to say 2. Oh, let's count from 0. Here, counting from 0. Then we're going to say 2. 1 is going to be north, southeast. 2 is going to be, oh, okay, is going to be north, southwest. And then we're going to say 3 is going to be north, northwest. 4 is going to be south, southeast. Oh, south, northeast. Sorry about that. 5 is going to be, let me see, south, southeast. There we go. Then 6 is going to be, sorry about this, guys, south, southwest. And 7 is going to be south, northwest. Good. Just so we have everything kind of set, so we know how it's kind of counting, we go to the top of the cube first, and then we count this way. We count clockwise, both ways. We just count clockwise. We start at the upper right, and we count clockwise. There we go. Fine, let's just go ahead and use the array. Personally, I prefer to define it as x. Wait, what? X greater than 0, 4. Y greater than 0, 2. Z greater than 0, 1. Wait, let me think. X greater than 0. So if we're over x, let's see. It's going to be 4. Oh, yeah. I could write that. Let me see. However, this one makes a little bit more sense to me. So let's go down here and let's do include array. I mean, I'm working on points. I mean, I can also put that in there. It's just, it's not the easiest to read. For me anyway. So let me see. What do we have here? Array. Then we want array up here. Let me see. Implicit back. Where are we? std array. node star 8. STD array of, let me see, node star 8. And we'll just call it child or something like that. What should we call this? Before I had children, I guess this is fine. This should be okay. Yeah, that should be okay. Whatever, I'm spending too long on this. Okay, so we have our node. Now what do we need to do? We need to... Children is better than child. But here we say child 8. Otherwise we say children 8, you know? Subnode regions. I mean, that's actually what it is, isn't it? But let me think. It's fine. It's fine. Let's... I'm spending too long squabbling about this. So now we're going to say function to create octree from position data. Okay. So what we need to do is return back a node. I guess just a node. Does it need to be a node star? No, I think node is fine. So node, and we're going to say create octree. And what do we need to read in? We need to read an std vector of positions. And we'll call this, why not, p position, like we did before. Okay, now what else do we need? That might be it. Just the vector positions. Yeah, okay. Let's see, box length. I guess we should read in box length, yeah. Yeah, so we should read in box length. So let's do double box length. Okay. I think that's fine. Good. Okay, so now what do we need to do? Let's go down here and let's create the function and work on it. Misspelled function. Okay. So let's grab this, pop down to the bottom, put it in. So let's see what happens. You know, this might take the rest of the day, I'm not sure. But if we can get the octree done by the end of the day, I'll be happy. We already have all the positions created in a random distribution. That's pretty nice. Now it's just a matter of going from there and finding the appropriate spots for everything. If we can finish the octree by the end of today, tomorrow we need to visualize the octree, which isn't going to be the easiest thing to do, but I don't think will be that difficult either. We just have to kind of think about things. Box length represents the length of the... it represents either this guy right here, or the length of the individual nodes on the inside. So it could be, let's say this guy's split. Wow, that... Let's say this guy's split up here. Each node has its own box length. So let's say I somehow drew this perfectly, and it was split up like this. Then the box length would be here. So I'll denote it as L here or L here. So it's basically the length of the internal cube. So let's see, something like this. 1 second. Something like that. That was bad. 1 second, something like that. I can't draw this very well, but the idea is, let me draw it on a quad tree surface. The box length is here, or it's the length of the nodes on the inside. So L here, or L here, so on and so forth. It's the spatial distance in which the box spans. So initially it's just going to be the length of the entire box, which in this case we set as 1, and then it will slowly get smaller and smaller as we get closer and closer to the center. Okay, so again, like I was saying before, we need to, and let me know if that makes sense, because if it doesn't make sense, Dr. Kegel, I need to describe it again. Again, apparently, like I said earlier on in today's episode, the geometrical optics stuff apparently wasn't the easiest stuff to understand. So if you have questions, please feel free to ask, because Again, I always tell people to ask questions if they have them, but like there's no such thing. You just don't ask. You cannot ask a stupid question, I don't think. So if you have a question related to the subject material, just feel free to ask it, because it's probably going to be relevant. Okay, so create octree. Let's first create our initial node. So creating initial node. And I guess we'll call this, let me think. So let me, this is actually gonna take some thought on how to do this, but it's not so bad. It's just a simple recursive type of thing. We're gonna have to probably read in the node is what we should probably read into the create octree. Okay, that's okay. Let's go from here. So what we're gonna say is node, no, we need another recursive algorithm inside of this one. We'll figure it out. We'll do it. So node, root. Each cube is cubic and box is square. Yes, they're all cubic. Because this is octree. If we were doing the KD tree, which is a very similar thing. In fact, here, let me just go here and look up KD tree. Things would be a little bit different. So let's do images. In the KD tree, the boxes are allowed to be different sizes. However, in the octree, they're all squares. Here, let me view the image. You might not have been able to see that. Let me zoom in. So here in the KD tree, they're allowed to be or rectangular or something like that. In the octree, they must all be squares here. Something like this. So hopefully you can see that. And I'll just go ahead and give you this image here. And this image here. Just so you guys have access to it in case you can't see it. But yeah, that's kind of the difference. Also, I mean, you can do KD through trees and 3D and stuff like that. It's kind of easier to find a particle's position with cubes, because then you know kind of what box lengths and stuff you're working with. Yeah, honestly, I was kind of debating between KD trees and octrees, but then I found the Barnes Hut algorithm, and honestly, guys, what ended up happening was, you know how I took yesterday off too? Like, I took the entire weekend off, and then I took yesterday off. I told you why, right? Like, so over the weekend, I spent the whole time editing my YouTube video, and on Monday, I took that day off because it was like Sunday night when I found the Barnes Hut stuff, and I was like, oh, that's super cool, and I wanted to do it, but I didn't really have time to do it, or time to look into it. So I looked into it yesterday, and I think I've got a good enough grasp that we can go from there. Now, the other thing is octrees are used a lot for graphics and stuff like that. Let's go here. Sorry for the yawn. To do, you know, kind of like positions of colors and things like that. I don't know very much about that, and that's not really what we're gonna be working on. But it's there in case you're interested. Octrees are used a lot for a number of different things. So what we need to do is create the root node. Okay, and I guess we'll just say node root, and then we'll say what we can do is we can also put in a how do I put here, a constructor real quick. So we'll do this. We'll say what do I want here? Node here, and we'll just kind of say that gives it the initial positions. So the initial positions are going to be let me see. We have a position P. So I guess let's say P.x. It's going to be 0.0. P.y. .y is going to be 0.0. And then P.z is going to be 0.0. Okay. Then we also want the box length, which is going to be 1. Going to be 1.0, just for standard stuff. Let's see, what else do we have here? Double box length node parent should be okay here. Okay, now let me go ahead and put it into a constructor real quick. So we'll say node, and we want, let's say position, P, location, And then we'll say next, what do I want? I want box length, so double length. Okay. And then we'll say this. We'll say P equals location. Oh, what? P is location. And then what do we want? We want box length is going to be length. Okay. Now, I'm trying to think here. We should probably also give it the ability to put it in a node star as a parent. So let's go here and let's add in node star. Here, and then we'll put in that as a parent. So what do I want here? I'm going to put it here and say parent is, oops, I did not give this guy a name. I guess I'll call it pair. And that's going to go here. Okay. Let me see. I guess I put this down here. Let's see what happens. Let's make that just to see what happens. P.x expected parentheses. What did I do wrong here? Node P.x before dot. Maybe I'm not allowed to do that. Am I not allowed to do that? Just initialize it like this. Let me see. I guess I should initialize it another way then. We'll initialize it like this. P of maybe something like position. Oh, G++. There we go. Okay, that one worked. Okay. So now we have everything set there. We might need to change the constructor a little bit later, but that's okay. We'll kind of worry about them when we get to it. So we're going to say node root. And I guess we'll say the following. Let me see. How did we do this before? We said position m place back. I guess we'll say equals node. Is this the right notation? Dagnabbit, I always forget. Okay. So that should be the initial location of 0, 0, box length of 1.0. Good, so that's going to be our root node. Now, we have to think about how we're going to divide everything. So I think I'm going to create another recursive node here, or a recursive function here, that does the, basically the dividing. Now I suppose we could put that all into our create octree guy, right? Where we don't initially... No, we should read in a box length. Wait, I have to think about how to do this. So let's go up here. We have a create octree guy. Here, it will return a node, which is exactly what we want it to do. But I suppose we should have it also read in a node. Yeah, so we give it a root node to begin with. So let's go here, let's read that in. We're going to say node. And let me see, vector position. I need to put an ampersand here. And good. So we're going to say node. And we will say... It's not going to be root, right? I made the mistake of calling it root last time. So we'll say, what do we want to call the node? We will call it, object, I don't know what to call it. Actually, this is going to be the node that we're currently iterating through with the octree. So the idea... here, let's go here. Initially, read in root node, I suppose. Okay. And I guess we'll call it... Shoot, what should we call it? Let's say... we're a position along the tree, right? So I guess node. Okay, I'm really bad at naming things, as you guys have seen so far. Let me see, create octree. It doesn't even make sense for this function. Here, let's just redo this. Let me redo this. Let me think about this again. We need a recursive algorithm. Let's go here. Initially reading the root node. So here's what we're going to do. We're going to say divide octree. Okay, now we're going to say node current. There we go. Reading in the current node. Need an ampersand before this guy. There we go. I love Twitch 1411. I do not accept tips, but I appreciate the sentiment. Like, it's one of those things that I understand people really, really like certain streamers and stuff like that, and I like the fact that you would be willing to give me a tip or whatever. But it's I'm financially stable right now. I don't need anything more, so far as I'm aware. Maybe like tomorrow, my boss comes by and just says I'm fired, but he's in Iceland right now, so I think that'd be a little bit weird if he just gave me a phone call and was like, oh yeah, by the way, you're fired. So, plus I think I have secure funding from the graduate school, even if that happens. So I'd be super worried if something like that happened. Okay, so good. So we read in the current node. Then what do? We give it a box length. We should probably also give it a position. Yeah, we should give it a position. Or, if we're reading in the current node that we're going to be dividing, yeah, maybe we don't need to do it. Okay, let's just do it this way, and we'll see how far we can get with this. At some point, this is gonna break. Okay, so let's see what happens. Divide octree. Let's go here, down here, done. Okay, so we're assuming we're gonna have a node. Now, we need to check to see how many particles are within our node. So that's what we need to do first. Determine number of particles in our current box. Okay. So, what are we going to do then? What we need to do is, well, just that. How do we find the number of particles in our current box? Well, we could just iterate through the vector of all the positions and find where all the particles are. Now, that's a little bit slow, and there's probably a faster way to do it. However, I'm not quite sure exactly what that is right now. Oh, no, what we can do is in every single node, we keep track of a vector of positions. Let's do that. Let's see, where are we? Struct position, struct node. Will our particles have radii? Radii? I actually don't know how to pronounce that word. Radii, I think. Will our particles have radii? Right now, no. However, I suppose maybe they should. If you think they should, I can add in a radii, that's fine. I can add in a radius to each of the particles. So let me go down here. Position P, and this guy's going to be the position of let's say the node slash box here, and then we're going to go down here and say positions of all particles in box. Okay, so we'll say vector positions. Remove this space over here, go down to the end. Oh, remove 2 spaces on accident. And we're going to say this as P position. Okay. Good. So let's go down here. And then basically, I think maybe this will take up too much data. There's probably a better way to do this. Radiuses? Is radiuses actually a word? If it is, that's perfectly fine. So determine the number of particles in our current box. So what we'll do, since we're reading in a vector of positions anyway, let's just go through all the vector of positions and let's check to see whether they are currently in the box that we're working with. So we have our the current node that we're working on. It has a length and it also has a position. I think, yeah, I've definitely seen radii before. Again, I'm terrified that I'm mispronouncing it for some reason. I have to look that one up. Okay, so let's do determine the number of particles in our current box. So we'll just go through all of the positions and we'll check to see if they're in the box. And then we'll increase the count accordingly. Now what we should probably do, is we should probably push back our vector. We'll hit it as we hit it. So let's do 4. We'll do auto ampersand p in all of our p positions. So p position. There we go. Now we're going to say, I suppose, if we're within the box. So if p.x is, let me see. I guess we need to find the box's bounds, right? So, or we create a separate function to say in bounds. So let's do that. Okay, so now we're gonna say, where are we here? I believe they're both correct. Former being later derived, Latin derived, and the other common English derived. Maybe fair enough. Yeah, you're probably right. So now we're gonna say function to check whether a position is within a box. Okay, so now we're gonna say Boolean, and I guess we'll say in box. And what do we need to read in? We need to read in the node. So we'll say current node that we're working with. Why not? And what else do we need to read in? We also need to read in the position that we're working with. So position P. Okay. So let's go down here. Drop it down there. Oh, that was just a capital G. G. Paste it here. Good. So inbox, how do we do this? Well, we go and we just determine if it's in the box. So let's do it. What are we going to say? We're going to say if, let's see, we have the bounds, right? Yeah, kind of. So I guess we're going to say if p.x is greater than, how do we want to do this? We need to say current dot position dot x minus current dot box length times 0.5. Oh, this is gonna be a pain, isn't it? And p dot x is less than current dot p dot x, where it currently is, plus box length times 0.5. Yeah, this is gonna be a pain. Okay, let's go down here. If you guys can think of a better way to do this, let me know. There probably is an intuitive way that I'm not thinking of, but that's okay. So let's pop this down here. And let's do this, add something there. Why is this so much smaller? Ah, it's because I forgot a current. 1 second, current here. Then we need to check for y and z. And if all of them are good, we return 1. Otherwise, we return not 1. And I suppose we should do greater than or equal to here. Yeah, sure, that's fine. So p.y is greater than or equal to current dot position dot y minus current dot box length times 0.5 ampersands p dot y is less than current dot position dot y plus current dot box length times 0.5. Okay. Now the last one's for z's. We're gonna say p dot z is greater than or equal to current dot position dot z minus current dot box length, and then we say times 0.5 ampersands. Okay, last one. And then at this point, someone's going to come in chat and tell me that I'm doing this way too incorrectly or something like that. I don't know. Current dot box length times 0.5. And that should be it. Go down here. Okay. So what are we going to say? We need to say return true. And then else. Hey, Bomb Mask, what's up? Return false. Let's do G++. Good, seems to work. A cube has no length. Kappa. Wait, what? Ooh, ouch. I keep freaking hitting my finger. A cube has no length. Kappa. Oh, good. Let's see. Red eye is 4299 most used English word. Radius is not amongst the first 86,800. Fair enough. So I've been thinking, is there a reason why you choose C++? Honestly, the reason I use C++ is just because I know it very well. Not very well, I know it decently well. You know, like, my languages of choice for numerical simulations are either C++ or Fortran because, quite frankly, they are the fastest ones. And, you know, some people will say one's faster than the other. It doesn't really matter. Nowadays, I think people generally say that C and C++ are faster, but for number crunching, they work quite well. The other thing is C++ has a bunch of additional features, so I kind of like using that over Fortran nowadays. The other thing is, I could be using... Could you not just return returns of the ands in C++? Wait, let me see. Could you not just return the return of the ands in C++? Probably can. Let me think. If return... Yeah, probably could. Okay, so let's go up here. So to finish answering your question, Bomb asked, a lot of other languages are kind of breaking into the C territory for numerical work, in terms of, like Julia, for instance. It's getting there, you know? And of course, a lot of people use MATLAB if you want to use MATLAB for specifically array stuff. And a lot of people use Python even for some things because it's got an extraordinary number of libraries. So as Sna said, just use what works best. If you have an idea of something that you want to use, that's what you got. Okay. Yeah, fair enough. So let's go here. And we can probably just do that. So let's do return. Let me see. He could also nest his checks to speed it up a bit. Which checks? Wait. What do you mean? No, sorry about that. Again, I'm not claiming that I know the most about... Let me think. I'm not claiming I know the most about C++. What do you mean when you say you want to nest my checks? So I assume you mean these guys in here. The equals to all of these guys. But I don't know what you mean by nest. Sorry about that. I suppose... No, I'm not sure. Sorry about that. Okay, so let me go here and let me do return. And I guess we'll see what happens. So let's just remove these guys. Remove that guy there. You should do one set of XYZ checks first. If it's outside the X space, you need to check for Y and Z space. Oh, I see what you're saying. Yeah, we could do that. You should do one set of XYZ checks, the other ones later. Yeah, that's fair enough. I was thinking about doing it that way. Actually, language doesn't compute all of... actually, the language doesn't compute all of the ands ifs one fails. Yeah, maybe that's true. Let's just go ahead, do this. Add a semicolon at the end. Let me see what happens if we make this. G++. Okay, it seems to make just fine. So, what do we need to do? If one fails, it's short-circuiting. That I don't know, but quite possible. Yeah, I don't know either, but whatever. Let's see what happens. So let's go up here and we'll say, what do we want to do? We'll say if return AA and BB and C. If A is true and B, C, and D is not evaluated. Yeah. I think we knew what you meant. So I used to love C++, which is why I'm asking, but I found that my turnaround time, newer languages, Swift and C# mainly, and you can prove that the speed of Swift is faster than C++, but the amount of features in the languages have a lot of benefits over older languages. That might be true. But again, what we're doing here mainly on this channel is scientific computing, right? So, because of that, we have certain restrictions on the languages that we would like to use, and it should be languages that, well, people know how to read, basically. And the other thing is, speed is one of those things that you can't really quantify very well with languages, right? So usually when I say speed, I mean like number crunching, Yeah, so that's the thing. I'm currently learning a lot of different languages. C# is probably not one I'll look into, and I haven't really considered Swift. We'll see where that goes. Okay, so let's keep working on this. We're going to say if, we'll say inbox, and we are reading in, I guess, the current node that we're working on, so we'll do current, and particle position, so let's do P. We go down here. Good. Let me see. Print line is a condition? Oh wait, where's print line? I'm sorry, I missed something. Let me see, print line. You can check it using something like this, false and print line text. Will not print the text. Oh, I see. No, it's good. Let me see. Bomb has appreciation sentiment, but Swift is never going to be faster than well-written C++. You can only reproduce Swift runtime, so in the worst case scenario, it's just as fast. No, it's fair enough. I see what you're saying, Lauren. Let me see. What do we want here? Print text. Yeah, we can look into that. I'm not going to argue that Swift and C++ are way more convenient than C++. Maybe. Not sure. I might have said C++ twice. Okay. If inbox, what do we do? Well, I guess what we do is we append its position to the position in current. Okay, so let's see what happens. Let's do... yeah, why not? For now, we'll just do pushback. There's probably a more efficient way of doing it. In fact, there must be a more efficient way of doing it. But we'll leave it as it is. So we're going to say current.p position dot pushback p. That's awful. It's fast. And also look at what Swift does. Well, Swift compiles down to machine code via LLVM. C++ and Swift should be about the same after compilation. I guess that depends though, right? Because if it kind of boils down to C++, I mean, in a sense, doesn't MATLAB do the same thing? Like, doesn't it have C under the hood or something like that? So in the end, it kind of just depends on how many abstractions you had to take from the language that you're working on. And here, what I want to do, let me see. Okay, so here's what I'm going to do. I'm going to, just to make sure that this current part of this is working, I'm going to return back current down here. Current. And then I want to go up here and I want to just go ahead and create our root node. So let's go here and say creating root node. Okay, so we're going to say root. 1 second, node root is going to be equal to node. And then we're just going to say divide octree. We're going to say root is going to be equal to divide octree. And what do we want to read in? We're going to have to read in all the particle positions, so p position. Then we want box length, which is going to be 1. And then we want node current, which is root. Okay. Let me see. Gustor, nonsense. It's like you're saying that Arab is better than... Okay. Swift still uses ARC, which is slower than manual memory management. Okay. So let's see. Root, divide, octree. Okay, here's what I want to do. I'm going to go in here and I'm going to output some stuff. Just to see what we got here. So let's do stdc out. Or print line. Let's just do exactly what we have here. Printf. There we go. Grabbing it, pasting it right here. Let's go into G++, Barnes Hut, and of course I forgot I. So these need to be just changed to P's. There we go. Now let's do G++. I expected a semicolon root. I forgot a semicolon here. give G++. Seems to run. A dot out. Okay, let me do a quick new line here. So let's do print f, I guess, something like this. Let's just do stdc out. A couple new lines won't hurt anybody. Now let's do G++, A dot out, and it looks to me like, yes, this is exactly what we want. I'm not going to compare C to Python, but Rust Swift comparison is pretty fair. Let me see, what are we talking about here? Swift and Rust. Nonsense is like you're saying, okay. Swift and Rust syntax is very similar. Apple decided to support it to be a viable competitor. Wait. If Apple decided to support which one? Swift or Rust? Sorry, Swift or Rust. I personally think that Chinese is better than Japanese. It's more object-oriented and uses garbage collection. Wait, the language? How does the Chinese language use garbage collection? Okay, let me see. What do we have here? I would just like to say that I disagree with the part that C++ will be faster. As an older language that is constantly getting more and more bloated from the scope creep. And the major attraction of C and C++ is its platform support and language maturity. Well, one thing you can't argue with is that for scientific computing, C++ is basically as fast as you can get, you know? Now again, Fortran is an obvious competitor, but between the two of them, you know, that's what people use for scientific computing. So they're the ones, those are the kings of scientific computing right now. Now, that said, other people are using other languages, but they haven't caught on yet. Julia is the closest one. Like, that's the one that people are kind of moving to. All arguments are moot because assembly. I gotta argue as a Linux user that C# is the worst option. 95% of games I buy do not work because have mono in there. Oh, I didn't know mono was C#. Interesting. Well, thanks for the information. Okay, so currently what we have is we have the ability to basically push back all the particles in a current box. Good. Okay. So what we need to do then is the following. So we're going to say if the particle is in the box, we will say we push back all the particles. All that's set. Now what else do we need to say? After this we need to say if... how do I say if there are no particles in the box? I guess we'll say if current... Wait, I have to think about this one. If there are no particles in the box, we don't do anything with the box. The box just stays there. But if there are particles in the box, so we're going to say if current dot p position is, let me see, dot size is greater than 1 after pushing everything back, then what we need to say is, what was that syntax? The following. Let's go here. C++ is pretty much all features very fast code. Wow, I just mumbled. C++ has pretty much all the features necessary to write fast code in C++ 11. The language's age doesn't matter as long as the new design doesn't enable some easy optimizations. I agree with that, but I have my hopes up for .NET Core. Wasn't that recently moved to Linux? I think so. I think if I'm following the conversation, I think that was recently moved to Linux. By the way, thanks guys for having such a good conversation. Like, this is the perfect conversation for a stream like this. Like, fantastic. I love the fact that you guys are debating different programming languages. Even if I don't know exactly all the different languages, like, this is a good civil conversation. At least it seems to be civil. And I like that. I like that you guys are discussing points and not arguing about them. You know what I mean? Okay. So if current position size is greater than 1, what we need to do then is we need to divide the octree further. So we will say, now the question is, how do I do this? We need to divide it further. Okay. So I guess we'll say, we need to divide the octree into 8 and read each one into, let me see. Yeah, the moment Java comes up, someone gets mad. Divide octree. And you know what, guys? I'm thinking about this. I think what I might want to do is immediately in divide octree, split it up into 8. I think that's what I want to do. So let's go here and let's go ahead and divide it into 8 up here. And then, how do I put this? Yeah, divide it into 8 up here and then go from there. Yeah, I think that's probably the best bet. Because if we're reading in the root node, I mean, the root node obviously has all the particle positions in it, right? So, it should be okay. So let's do this. We're going to say, this. So we are going to divide node into 8 subnodes, boxes to work with. Okay. So we take our node and we divide it into 8. This means that the box length is going to be cut in half. So we're going to say, let's say, double node length is going to be equal to box length divided by 2. Okay. And let me see. So it's hard to go from Java to C++. I was just about to write a Java comment about learning C++. No, Java or net runtimes from my computer, I'm good. Let me see. From what I can tell, your description of Swift does not do the same. Okay, so what are we going to do here? We have the node length there. And actually, guys, we might only need to read in this. Again, I apologize for kind of hopping back and forth. Kind of writing things from scratch here, and so I need to kind of think about things as we go along. And of course, people rewatching this, if there is anyone rewatching this, sorry, you can just skip through some of this stuff, because here we're just kind of thinking about how to do everything. So we have the node length there. Now, we have our array of 8. Let's just go through, and let's give all of these guys appropriate positions. So, how do we want to do this? We could create a separate function that reads in the node and returns back the 8 children node, and I think that's probably the cleanest way to do it. So let's do it that way. Let's go up here, and let's say function to divide, create 8 children node for octree. Okay, so we'll say node or void, and we're going to say make octopus children. Yep, that's good. Node ampersand current. There we go. Exactly what we need. We'll leave it. Okay, let's do it. So make octopus children. Let's do it. I'm sorry, guys. Okay, let's do it. Node current. Let's go down here. Let's grab our function from up there. I think it's capital H. There we go. Capital G. Okay, so we're reading in a current node. And let's do it. I keep saying let's do it. Like, I should be getting money from Nike or something like that. So, because we're reading it in with an ampersand, it should go ahead and, 1 second. So make oct. There we go. G. Okay. Again, I have to apologize for how slow I'm moving. I realize I could be moving faster. So make octchild. What are we going to do? We're going to take in the current node. We're going to divide it by 8. So I guess we'll do exactly what we did before. We're going to say double node length is going to equal to current.box length times 0.5. Okay, so now we're going to create the 8 nodes. You're right. You're right. Okay. So if we create all of the nodes and we point them to the parent node and we point, yeah, good. Okay, so let's go through and let's create all the children. So we're going to say for int I equals 0, I less than 8, yep, plus plus I. Okay, so we're just going to create a node and we're going to point it to the appropriate position, I think. Right? I think that's okay. Or we do it this way. Let's do it this way. So we'll say for n auto ampersand n in, what do I want here? I want current dot children. Okay, so we're going through all the children. Yeah, you're right. You're right. So going through all the children, and now we just have to update each of these children, I think. What's the worst that could happen? Okay, let's do it. So we're going to say n dot box length is equal to node length. Good. Now we need n dot position, which is actually going to be a bit of a pain. Okay. So how are we splitting this guy up again? We're splitting it up into 8. So I guess it's going to be equal to this isn't exactly obvious, is it? Okay, so let's do this. Let's say if and I know there's a more efficient way to do this, but for now let's write it this way. So we're going to say if okay, let's do it this way. Int I equals 0, I less than, gosh darn it, current dot children size plus plus I. Now we're going to go down here. We're going to say current dot children of I dot box length. We're going to say if I is less than or equal to 4, then we're going to be in the top box, and else we're in the bottom box. Say splitting into 2 boxes, top and bottom. Okay. And of course, if you guys have some intuitive way to do this, let me know. Otherwise, I'm just going to brute force it. So if you listen forward, what we're going to say is current children of I dot p dot z is going to be equal to, and it should be current dot box length. Let's see, times 4. Times 0.25, sorry about that. And we want to do current dot p dot z plus current box length times 0.25. And that should lift it up by about 1/4. Of course, down here, we're going to say the same thing except minus down here. Okay. Any particle at 0, 0, 0 will create a new universe. Wait, why? Okay, so this should be okay. Now we have to do the x's and the z's. So what we're going to say Okay, so now we have to cut it along this way. So we already cut it along this way. We have to cut it along this way now. So we'll say in here, if I, we go up here, remove the space, is less than or equal to, this has to be less than, doesn't it? It has to be less than. Less than or equal to 2, okay. Yep. Yep. This is bad. This just looks ugly. There's no way to make this not look ugly. And then we need another one in here with if I mod 2 equals 0. Oh man, that looks horrible. It's fine, let's do it. Okay, let's go down here. We're gonna say current children, basically copy this, change it to x's. So, p.x, is it x's? Yeah, it's x's. Rx. Rx, good. Now we do the same thing with y's. P.y. Okay, this is quite bad, but that's yeah, okay, that's fine. So what we'll say is if it's less than 4, that means we're either 0 to 3, so we're at the top. Then we say if it's less than 2, which means we're either 0 or 1, we're going to say it is splitting this way. Then we're going to split this way from there. Yep. Else. Yep. Yeah, this is quite bad. Let's do that. Okay, so now we need to change this to a minus. And then we have to add something in here real quick. Else. Yeah, brute forcing it was a bad idea. I'll think about this some more tonight. So we're going to take this and put a minus in. But I think this will work. I mean, it's just a bunch of if statements, right? So what's the worst that could happen? Okay, good. Woo. Okay, so now we're going to do the same thing down here. Okay, now let me think. We're going to have to change the bounds, but I think the internals are all going to be similar. So let's just grab this. You definitely don't need the for loop. Why not? I'm actually genuine. I can't think of how to do this without a for loop. I don't really understand what you're doing, but just so you know, I mod 2 equals 0 will only trigger at I equals 0. Yeah, that's right. That's exactly right. So we should have one that is good and the other that's not good. It'll trigger at 0, 2, 4, and 6, which is what we want. I think this should work. I don't understand why I wouldn't need a for loop, so if you have an idea of how to do this without a for loop, let me know. I'm probably just majorly overcomplicating things. So we're going to say if I is less than, let's say 6, then I think everything else should be set. Okay, so let's go here, write this, go over here, G++. Okay, broke something. Let me see. Error request for member box length. And let me see, what do we have here? Current. Okay, so now we have that issue with all the freaking pointers. Let me see. So the idea was that we split the box first here and here, then we split it here and here, and then we split it here and here, if that makes sense. So what I wanted to do was take 4 up here and 4 down here, then take 2 here and 2 here, 2 here and 2 here, and then take 1 of each, if that makes sense. So Pretty sure I'm majorly overcomplicating this. So let me see. What I need to do then is, what do we have? Current children I pointing to PZ. Maybe this is right. Let's see what happens if we change all these to pointing tos. So what I need to do is the following. So let's do big R. There. Okay, so let's change all these guys. Oh, oops, that wasn't what I meant. Shoot. Yeah, let's do it this way then. And I might get to a point where this compiles and then just call it for the day and think about it some more on my own. So let's grab this. 1 second. And of course, guys, as I mentioned many times before, I don't claim to be some sort of... Shoot. I don't claim to know everything. Obviously, I don't know very much at all. So if you have any questions, let me know. And we can totally address those questions as they come up. Another thing I want to point out, if you have additional ways to do this, all we're doing is dividing up the box. There is most definitely a more efficient way to do it. Let me think. So let's go here. Let's G++. Okay, so we still had an issue here. I just don't know how to do it without an I. That's the thing, I can't quite figure out how to do it without some sort of like some sort of I to put it into the right spot. But we can probably figure it out. Yeah, we'll see. Okay, so let me see. Invalid initialization of non-constant reference of type node ampersand from an R value of int. Root equals divide octree root. Invalid initialization of non-constant reference of type node ampersand from R value of int. So let me go and see what we did wrong here. So let's go to divide octree. Here, let me see. Node int. Passing argument 2. Oh, yep, I know the problem. I removed something. Where's divide octree? Oh, it's up here in main. Remove the 1. G++. Okay, this one works. Sorry, you're only doing Y's 1 by 1. Others. Okay, so how would I replace the mod 2? What else? What would you think of? Let's go down here. Oh, that was in the wrong terminal. Okay. Yeah, I could replace them with something else. So let me see. Instead of mod 2, I could say, let's see, if it's less than 2. Oh, dagnabbit. I'm missing a couple cases here anyway. I'm totally missing a couple cases here anyway. Because here's the thing. We split into the top 4. And then we split it into the bottom 4. Oh, actually, no, this is fine. This is fine, this is fine. Top 4 here. And then we say, split it here, split it there. Every mod 2 is exactly true at 1 number. Wait, let's do this. Okay, so let me go over here. Page, new page before. Ah, shoot, I'm running out of time. Okay. So what I'm gonna do, I'm gonna say I greater than 4. Less than 4, whatever. So we're in the top box here. I'm just gonna draw a box here with my fantastic box drawing skills. Okay, so now we have boxes 0, just arbitrary numbers 1, 2, 3. Okay. If we say less than 2, we're drawing a line here. So we're in this box or this box. And then the reason I did I mod 2 was because I mod 2 would naturally grab these two guys here. This one and this one. I can't think of a way to do that without a mod. Oh wait, maybe I can. Let me think. So let me go back to the code real quick. I'm on 2 is equal to this. So if I is less than 2, we do this else. Oh, I did it wrong. 1 second, it should totally grab those. If I is less than 2, else. Why does using normal recursion here? And keeping track of the depth? Probably because there is a way to use that and I couldn't think of it. I just didn't think of it. Let me think. Honestly, I think this is right. It should work. But let me see. If I is less than 2... Yes, exactly I equals 0. That's exactly what I want. And if it's greater than 2... Oh, I see what you're saying. So what you're saying is you just want to do this. If I is equal to 0... Sure, we can do it that way too. I equals 2. I equals 6. 4. And I equals 6. Yeah, I see what you're saying. We can do it that way too. Yeah, that works too. Okay. Well, this is kind of messy. The mod code can be put at the end. Okay. That should be fine. Okay, so guys, it's 7 o'clock in the morning. This is about the time I typically end my stream. I apologize that this is so messy. Like, it looks messy, and there isn't really much I can think about, or I can't really think of ways to clean it up. But Krams, you apparently have an idea too. So if you guys want, feel free to let me know tomorrow what ideas you have on how to clean this up a little bit. Again, at this point, we're most of the way done, I think, with making our octree. We just have a little bit further to go. And I'm quite happy with how far we've gotten. I mean, 181 lines, 2 hours. This is quite good, I think. We're getting there. Now, that said, I need to add in a whole bunch more comments, a whole bunch of things here and there. It's certainly not to the point where I would commit it to GitHub. So, I'm going to leave this on my own. Well, actually, wait. Do you guys want me to commit it to GitHub? I can, if you guys want me to. Just so you guys have access to it. Let me know. And then after that, I'll go ahead and end the stream. So, I suppose it's probably good. I mean, my GitHub stuff's so messy anyway. I might as well go ahead and commit it, right? I mean, what's the worst that could happen? So we have divide octree. Let me just go in here and write a quick note here, which is note currently not dividing. Let me go up here to the top, and let's write the note up here too. Oh, 1 second. Note. Divide octree will come tomorrow. I think. Soon. TM. No TM. Let's do this. Okay. So I didn't see you guys specifically mention that you want it on GitHub. So I'm going to leave it off GitHub for now, and we will work on it again tomorrow. If you guys have ideas on how to fix things up, let me know, because I will totally do my best to incorporate those ideas as they come along. Outside of that, guys, thank you so much for watching. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, where we continue working on the Barnes Hut, octree stuff, and then the Barnes Hut stuff. So my current schedule, I think we're going to get the octree stuff done first, take a step back, do some force integration, and then put it all together for Barnes Hut. There isn't so much more to do after that. So once the octree stuff is done, it's a matter of visualizing that, getting the force integration stuff in, and then we're good from there. Hey, Clone Style, you too. Have a good day. Okay, that's it. Thanks again, guys. See you around. Bye, guys.